This is my second stoichiometry video, and I will cover mass-to-mass problems, and those include volume and percent yield. So for this first one, what mass of aluminum bromide can be produced by the reaction of sufficient aluminum sulfate with 8.75 grams of ammonium bromide? All right, we can start getting formulas for these things. All right, so we have aluminum bromide. Aluminum has a +3 oxidation number. Bromide is bromine with a -1 charge. Now it says can be produced, so that's going to be on the product side. This will be one of the products. Now by the reaction of sufficient aluminum sulfate, aluminum's +3, sulfate is SO4 with a -2, and ammonium bromide is NH4 with a +1 bonded to bromine, that's a -1. Now, this word sufficient, don't let that confuse you. It doesn't really change how you do the problem. What it's saying is you have two reactants in here, aluminum sulfate and ammonium bromide. I only give you the mass of the ammonium bromide, and that's really the only mass you need for this. The sufficient is getting into what's referred to as limiting reactant. When you have a reaction written down, the formulas, you have it all written out, it makes it seem like you have the exact amount of each reactant to completely react with each other to get consumed to make the products. In reality, that's rarely the case. What usually happens, what almost always happens, is one of the reactants gets used up first. And then once that reactant is used up, the reaction stops occurring because you're not getting these collisions between the reactants anymore because one of them's gone, one of them got consumed. The one that gets consumed is called the limiting reactant. And that's the one that would really dictate how much product you would be able to make. So this word sufficient here really just means that this 8.75 grams, that is the limiting reactant. That is the one that would get used up first, and then you have enough aluminum sulfate in there to react with all 8.75 grams of ammonium bromide. So the word sufficient doesn't really change how you do the problem. You're still going to start off with that 8.75 grams of ammonium bromide, and we're going to convert that through a stoichiometry problem to get the mass of aluminum bromide. So we have to get the reaction down. So what we end up having is aluminum sulfate. So we get Al2SO4 in parentheses with a 3. And that is reacting with ammonium bromide. And the way I'm getting these, just like in the previous stoichiometry video, is by crisscrossing the oxidation numbers, stuff we've done before. So since ammonium and bromine, they're +1 and -1, the ones just cancel out. The Al2SO4 well, this 2 here is really coming from that charge on sulfate, and this 3 is coming from that charge on aluminum, stuff we've done for a while when you crisscross the oxidation numbers. It's telling you aluminum bromide is one of the products, but we should be able to figure that out anyway. You have this aluminum that is going, this aluminum here that was bonded to sulfate is now going to be bonded to the bromide. So when you crisscross the numbers, you get AlBr3. Now, there's another product in there, even though the wording doesn't tell you, but this ammonium is going to end up bonding to that sulfate. So when you crisscross those oxidation numbers, you get the ammonium, the NH4 in parentheses with a 2 outside, and the SO4 follows that. Now we have to balance this. And this one sometimes tricks people a little bit, depending on what you start with. I'm going to start off with the aluminum because I think that will work well. So you have 2 aluminums on the left, you put a 2 here on the right. Now that gives you 6 bromine, so you put a 6 there. Now that gives you 6 ammonium. Here you have 2, so I'm going to put a 3 in front of that, and then that also balances out the sulfates because there's 3 on each side. If you started off with something other than aluminum, the process would be a little different, but you should still get the same answer. Alright, so this is telling you 8.75 grams of ammonium bromide. So we have 8.75 grams. And it wants to know what mass of aluminum bromide can be produced. So I'm going to put a question mark in grams. So this is clearly mass to mass. You're starting off with grams and you're ending up with grams. So let's start off with the number I give you in the problem. You have 8.75 grams of ammonium bromide. Now, these stoichiometry problems, mass to mass, they're all basically going to be done the same way. You're going to need 3 steps for this. And there's a reason why you need 3 steps. One is that all of these things have different molar masses, right? So, for example, the example I gave in the other video, I think, if you have 10 grams of carbon and 10 grams of aluminum, you have the same mass, but you actually have a different number of particles. You have a different number of moles. So we have to take that into account for both of the compounds we're talking about. NH4Br and AlBr3 have different molar masses, so we need a conversion factor for each one of those compounds. That's 2 of the steps. And then another step is the mole ratio. What's going on here is 6 moles of ammonium bromide will produce only 2 moles of aluminum bromide. So we need that mole ratio step in there first. Well, not first, also. The first thing you want to do is that you start off with grams of ammonium bromide, write grams of ammonium bromide on the bottom in the next step. Now, there is no conversion factor to let you go from grams of ammonium bromide to grams of aluminum bromide, or even to moles of aluminum bromide. What you have to do first is convert to moles of ammonium bromide. Now, this is just a conversion factor. This involves the numbers off the periodic table. The molar mass of ammonium bromide is 97.9 grams. All right, now you could get an answer here and then multiply that answer by the mole ratio and then get an answer there and multiply it by the other conversion factor. I'm going to put them all in the one step. It's quicker that way. It involves less rounding, so less chance for an error with that. So now you have moles of NH4Br. We want those to cancel out. So you have moles of NH4Br. We want to convert it to moles of AlBr3. Again, you can't go from moles of NH4Br directly to grams of AlBr3. There's no conversion factor to let you go from moles of one thing to grams of another. You have to get the mole ratio. And these are the numbers you get from the coefficients in the periodic table. You have the coefficients from the balanced equation, You have 6 moles of NH4Br, so that goes here. You have 2 moles of AlBr3, and that goes there. So now what we have is grams of ammonium bromide cancel out, moles of ammonium bromide cancel out, and what we're left right now is moles of aluminum bromide, but we don't want moles of aluminum bromide. We want to go to grams of aluminum bromide. So now this is a conversion factor. The number 1 always goes with moles because it's how many grams are in 1 mole. And off of the periodic table, aluminum bromide is 266.7 grams. Aluminum is 27.0. Bromine is 79.9, but there's 3 of them. So you multiply that out and add them all up. Moles of aluminum bromide will cancel out. Now what we end up doing is 8.75 divided by 97.9 multiplied by 2 divided by 6 multiplied by 266.7. Let's make sure I did this right. Alright, that ends up giving you an answer of 7.9456 and a whole bunch of numbers. But this is 3 significant digits. So we want our answer to be in 3 significant digits. So you get 7.95 grams of aluminum bromide as the answer. Alright, that's 3 significant digits. So all these stoichiometry problems are going to be done basically the same way. The first step is going to be a conversion factor. That is going from the grams of whatever compound you're given first to moles of that same compound. Then you're going to do a mole ratio, going from moles of that original compound to moles of the compound you're looking for. These numbers you get from the balanced equation. And then the last step is another conversion factor. It's going from moles of the compound you're looking for to grams of that same compound. You multiply the stuff across the top, divide by the stuff on the bottom, and that will give you your answer. Now you could do 3 individual problems here to get the same answer at the end, but like I was saying, it takes longer because you have to write everything out and round off the answer each time, and then with all that rounding, your number could vary a little bit. Alright, let's look at the next one down. Alright, now this one brings up volume. What volume of chlorine gas will react with antimony to produce antimony trichloride? Alright, well, chlorine gas, that is diatomic, so that's Cl2. It's reacting with antimony, which is just Sb on the periodic table, and antimony trichloride. With that prefix in there, it is telling you that it is a covalent compound. There's no charges you have to look up. There's no prefix for antimony, so that's saying 1 antimony. Tri means 3, and that's going with chlorine. So it wants to know volume of chlorine gas, and it gives you 165 grams of this antimony trichloride. So if you want to produce a certain amount of product, 165 grams, it's basically saying how much chlorine gas are you going to need to get that 165 grams of product. So start off the same way we have before. Write down the number I give you, 165 grams of SbCl3. Get into the habit of writing the units and the formula for whatever compound or element it is, because if you don't put that in there, it's going to be very easy to make a mistake. Alright, so you have grams of antimony trichloride. That is going to go in the denominator in the next step, and this is just like the problem above it. You can't go from grams of antimony trichloride right to liters of Cl2. There's nothing that can do that all in one step. What you have to do is go to moles of SbCl3. And this is the conversion factor. It's converting grams to moles of the same compound. Antimony trichloride off the periodic table is 228.3 grams. So now grams of SbCl3 will cancel out. What you're left with is moles of antimony trichloride. So that goes on the bottom. Now, you can't go from moles of antimony trichloride directly to liters of gas. There's no conversion factor to let you do that. So what you have to do is the mole ratio now. You have to go from moles of antimony trichloride to moles of chlorine gas, and you do this by using the balanced chemical equation, which I was going a little too fast and I forgot to balance it first. Try to remember to always balance these first. When I'm doing these on the board, for some reason I forget that a lot of times. You have to have these balanced because this mole ratio step is where you need those coefficients. So it's 2 moles of antimony trichloride for 3 moles of chlorine gas. So now moles of antimony trichloride cancel out. And what we have now is moles of chlorine gas, so that's going to go on the bottom. Now the difference in this problem is I'm asking for liters, and that actually makes the problem a little easier because you don't have to get anything off the periodic table. Whenever you are working with a gas, and I don't care what the gas is, the conversion factor becomes 1 mole of a gas equals 22.4 liters. It doesn't matter that it's diatomic. You don't multiply that 22.4. It just stays as 22.4 regardless of the gas. Alright, so now moles of Cl2 cancel out, and you do that math, 165 divided by 228.3 times 3 divided by 2 times 22.4, and you should get 24.3 liters of Cl2. Now I rounded it off because that's three significant digits, so you want your answer to be 3 significant digits. You get 24.3 liters of Cl2. Alright, the percent yield, I am going to save that for another video.